Okay, we're going to talk on light, optics, and some on vision, but that will actually be in a later video. Light, which is perceived, which we can perceive through our eyes, has a duality aspect. It's very heavily investigated in physics. It travels about 186,000 miles per second in a more of a vacuum area. So it's a very detailed topic, more especially discussed obviously in physics. But this, we're just giving an excerpt here so you can understand vision in later videos. So the duality of theory of light is it travels in quanta known as photons, particles of light, but it also travels in waves. So when you look at the wave theory, is the difference between wave and particle nature is that the wave nature of light explains that light can behave as an electromagnetic wave, and we'll be discussing that, whereas the particle nature of light explains that light consists of particles, which we said called photons. Your eyes respond to visible light, and visible light is part of what we call the electromagnetic spectrum, which includes other objects that travel in waves. The electromagnetic spectrum includes all energy waves from very long ones measured in meters to very short ones measured in nanometers. Visual light, the light that the human eye can perceive, is included in this spectrum. Its wavelength is 400 to 700 nanometers. Visible light, termed white light, contains various colors, the colors of the rainbow, each having a different wavelength. So right here are the colors of the rainbow, and here's a prism that can split the light into the various colors of the rainbow. Right here is a picture of the electromagnetic spectrum, and the spectrum is listed in such a way here, this is in nanometers, where gamma rays are in the shortest wavelength, and they travel as in the fastest frequency, whereas down here would be radio waves, which are longer waves. Now, the shorter the wavelength, the faster the frequency. The shorter the wavelength, the faster the frequency, the more penetrating. So gamma rays are very penetrating, short wavelength. When we come down here to visible light, see, visible light, the shortest wavelength is violet. That's why right above it, and that's the one we can perceive with our eye, but we can't perceive the one above us. That's why they call it ultraviolet, because it's a shorter wavelength, higher frequency than violet. Down here is red. Red is the longest wavelength that we have, less frequency, and right below it you can see is infrared, okay, which we cannot see. So this shows the colors that we can see, but what we actually see with our eyes is white light when light is coming in. But due to how light behaves, so here's how light behaves. If it's an object that's black, the white light would hit the black object. All the light would be absorbed. None would be reflected back to the eye. That's black. If the object is white, it would hit the object and reflect all the light back to the eye, which would still appear as white. So black versus white. If the object is red, this is what would happen. It would absorb all the other colors of the rainbow and only kick back to our eyes that's red. So whatever reflects back to our eyes is what we see. Whatever doesn't reflect back and is absorbed, that's what we don't see. Okay? So we go further. Again, we saw that. So we go now to the refractive index. The refractive index is a measurement. It's the ratio of velocity of light in a vacuum, okay, which I said light can travel fast, 186,000 miles per second, to its velocity in a specified medium. Okay, that's refract. So it's a measurement to compare different mediums. Okay, obviously, the more dense the medium is, the less velocity that the light can attain going through it. Refraction is the bending of light rays. And why do light rays bend? They will bend if they hit something of a different refractive index, and they have to hit it at a different angulation to bend into separate colors. So if it hits something that's a total right angle, then it won't necessarily bend, but it will slow. But it won't bend and separate out the various colors of the rainbow. So it's due to this change in velocity and the angulation that occurs. Okay. Now, curved lens can refract light. So this would be an example of curved lens. Okay. The curved lens can refract light, but if it's a concave curve, it will refract the light, disperse the light outward. If it's a convex, like you see here, inward. This is the kind we have in the lens in the eye. Okay. All right. Now, we go further. So here's the prism. Now, what I want you to do is to be sure to watch this. This is a great video to understand why when light hits a glass prism, it will display out into the different colors. And it has to do with the light hitting the angulation of a different medium, slowing, because all these waves are superimposed on one another. You can't see them until you bend them into their different wavelengths. And so you're bending at two faces, this face, which is an angle oblique, and this face, which is an angle. And that's what does it. But within the prism, it is spoken of that this light is hitting electrons. And so how it bounces on the electrons will determine how it splays out. But a great video to watch that I would encourage you to watch to further understand before you go further in my work here. Okay. Now, the dispersive prism that you see here is used to break up the light into constituent spectral colors because of this refractive index and this angulation. So once you watch this video, you will even understand better this right here. Okay, we go a little further here. So here's the visible light, 400 nanometers to 700 nanometers, and we're looking at it with our eyes. So what happens in the retina of our eye, discussed in a different video, we have rods and cones. The cones are really for color vision. And the rods really are for dimness of vision, black, white, and dimness of vision. Rods can perceive really just one photon of light. Okay, so we go further and we'll discuss this, but more exactly in a different video. All right, here you can see a different refractive index. See right here, this air-water interface makes the straw look like it's bent, but obviously you know it's not bent. Okay, so light passing through a convex lens, okay, let's go here. Light passing through a convex lens causes the light to bend and go to a focal point. The image that is perceived, the image which would be on the retina when we get to it, is called the real image. However, I want to go here though. When light goes through this lens right here, it goes opposite, which means that the top of the object you're seeing now is the bottom, and the bottom is the top. So it goes into that. That's how it would go to the back of the eye in the retina. That's how it would go. The left would be on the right. So everything is opposite. So the brain has got to come in and reconstruct it in the right form, which would be as you remember, the occipital lobe of the brain is where your vision activity is. So the actual lens and the eyes are sitting in a opposite activity, which means top, bottom, bottom, top, right, left, and the brain has to reconstruct it back into its proper imaging. Okay, so we go here, which we just saw, and we say that the pathway of light, now remember this refractive index aspect. So the pathway of light hitting It's going to pass through several refractive indexes. It's going to pass through the cornea, as you know, that's the first one, then the aqueous humor, that fluid, then the lens, then the vitreous humor, then the neural layer, and then the retina, and then the photoreceptors in the retina, which are really inverted. Actually goes through the back of the fibers before it gets to the business end, shall we say, where it's perceived. The cornea, which does not change shape, it has the majority of refractive power. So this is what I want you to understand. All of these others, the cornea, the aqueous humor, vitreous humor, the neural layer, and everything else stays constant. Assume it stays constant. So the only way we can see distance and close up is we have to have something to change the shape to bend the light differently. What is that? That's going to be the lens. So the lens is really your focusing aspect. Like in a camera, the lens is really the focusing aspect because the lens can get thicker or it can get thinner. The thinner the lens is, then distant vision. The thicker it is, it bends light more to give a near vision. Okay, but the majority of the refractive power is the cornea, and that's because that's the first air interface with your eye. But again, it can't change shape. Okay, so we go further then. So when we look at vision, as far as near vision, so forth, I'm gonna come here. What we will see is that if I want to look distant, and distant is your default drive, that's the easiest to see. I mean, in the normal eye, that's the easiest to see because the ciliary muscles would be relaxed. Ciliary muscles in the iris area would be relaxed. They would be relaxed, and what would happen is that would thin out the lens. Once the lens is thinned out, then the light can come back and go focal point back here, inverted image, and rest on the retina. Okay? Now, when it comes to control of near vision, the sympathetic nervous system is responsible for your distant vision. What does the sympathetic nervous system do? The sympathetic nervous system would cause the muscles, the ciliary muscles, to relax. Okay? It would also cause dilation of the pupil, ciliary muscles relax, and so you could see distant. Sympathetic nervous system. If I want to look close up, that's a harder deal because you got to contract the ciliary muscles Ciliary muscles being contracted would tighten down, which would squeeze down, called the zonule fibers here to relax more. And what would happen is the lens would get thicker. That would allow a better bend because I need more bend if it's close up. You see, I need more bend to come in on that focal point there. That's parasympathetic. So what does the parasympathetic nervous system with its acetylcholine do? It would cause the ciliary muscles to contract. So acetylcholine. Now go back and think about the sympathetic. That would mean norepinephrine would cause relaxation. So this would then do that, and it would also cause the pupils to constrict. The purpose of the pupillary constriction aspect is to keep aberrant light from coming in and interfering with the image. Okay, so that's what we're looking at. Okay, sympathetic, parasympathetic. So sympathetic, distant, parasympathetic, near. Sympathetic, distant, parasympathetic, near. Okay, I'm going to close here and start another.